here in the room with us as well as online. So we're going to see how we do with the hybrid process. Welcome. Today we will be talking about Statistical Process Control, or SPC. I'm Tanya Hulse. I'm the Director at Training Leadership Consulting TLC, and we partner with the PMCB to run the Lean Forum. And we run this probably, about 3-4 times a year, together with supporting PMCB with the annual Lean Conference, KZN Lean Conference. And so we use this Lean Forum as an opportunity to converse about one or more lean or operational excellence related topics. And with technology now, we can bring in people from anywhere and share with people from anywhere. So today we have the privilege of having our regional director from Gauteng, Maurice Kuhn, who will be joining us online. He's one of our senior master black belts who works with some of TLC's top clients around the country and beyond, running Lean Six Sigma courses, programs, coaching on Lean Six Sigma projects, delivering on consulting on using Lean Six Sigma tools, change management, leadership development, etc. And so Mo is very familiar with the concept of SPC, how to derive it, but also how to use it to deliver value in your company. So I'm going to hand over to Mo, who will talk us through it. I think we want to have it as a fairly interactive thing, but of course, while Mo is presenting, it might be difficult to see hands up or whatever. So we can just chip in and, we'll say, Mo, it looks like there's a question, and then there should also be time for questions and stuff at the end, hopefully. So let me hand over to you, Mo, and let's run with it.
Cool. Thank you. Thanks, Tanya. Appreciate it. Welcome, everyone, and thank you for the privilege of being able to be online with you. I hope that in the short time we have together that there will be something that you hopefully learn. Sometimes it's not about learning new concepts, but it's about different angles how we expand our angles that we look at something from. And I always find it interesting, Mark Twain said, if I had more time, I would have written a shorter story. It's not difficult to put slides together, but it is difficult to condense a topic like this one into a few minutes and a few slides. And I'm very aware that the folks that we have online are from different companies. It looked by a quick glance that I looked at that mostly manufacturing, less so service, the last list that I looked at. But I do want to say that these concepts are being used even more frequently these days in the service environments. And so that's one of the myths that people have and why they stay away from things like statistical process control, is that they believe that these concepts are limited to the manufacturing type of environments. So I'm going to be talking about some of the myths as I go through the slides. I think some of the understandings that people have, one or two places where we confuse some concepts, and hopefully that will lead to some discussion. I do want to leave some room for discussion at the end. So if I do go through some of the concepts quite quickly and you want me to gravitate back to them, you can either use that time in the Q&A afterwards, or you can stop, and if I know that something's coming and there's a slide that's going to support it, then I'm happy to handle that. So this is really just an introduction into the concept of statistical process control. But maybe let me ask you guys right at the offset, and you can either type that into the chat for me if you want to, or you can just raise your hands and I'll give you a chance to talk through it. But what do you understand by the concept, if you hear the word statistical process control? What does that mean to all of you? Any takers?
I'll pass it to Grant first.
Sure.
Well, I think, any processes that you have in business, it's not just down to, as I think Maurice mentioned, sort of your factory type sort of thing. Your processes is your business. So from taking on your new business clients to, how that client is processed, how you continue to deal with that individual, and it's understanding those processes. Statistics are very, very important in business. And the problem is a lot of people aren't in a position to be able to understand what they are because they don't have the resources to be able to find those statistics. So yeah, that's basically what I would say might have been.
Sure. Yeah, thank you, Grant. I appreciate what you just said, and I think that a couple of good points that have come out there is the fact that people very often don't know how to access the data side of it, and therefore veer away from it completely. And it's often easier to say it doesn't apply than to say, well, I actually don't know. Because I don't know looks like I don't know. It feels like I'm quite vulnerable, and maybe I feel like I look incompetent. So it's easier to kind of say, well, it doesn't really apply to us, and whereas if we do accept that it does apply, it could really go a long way in helping us in our understanding and decision making around our processes. So thanks for that input. Anyone else want to take a stab at it? Statistical process control, what does that mean to you?
I think it's in those 3 words. You're basically trying to control your process with data.
Perfect.
The process being anything from managing a business to managing a specific operation to managing whatever, but it's basically trying to control your process using accurate data.
Okay. Wow. Very rich words there. Controlling your process using accurate data. Yeah. Because fundamentally what we churn out is only as good as the data that goes into it, right?
Absolutely.
And I think that often business struggle with that. We either got people that are good at getting numbers and then turning them into charts and graphs and everything else, and nobody ever asks, whether the data is good or not. And then we've got folks that are good at collecting the data, but then sit with this rich data and say, we know in all of this there's some value, we just have no idea how to extract it. It's like digging for gold and saying, well, we bought the ground up, but we really have no idea how to sift through this and get the gold. So, so 2 very good points there. Thank you. Anyone else? All right, so let's move on quickly then. I think very, very important, statistical process control, those 3 words, very important, and kind of defines it for itself. So I've got a video for you. It is a fun video. I do want to put like a disclaimer on the front that says beware of, what might be offensive language to you and so on. But this was a video taken by somebody out of a window, looking at a bunch of cement workers. And something went wrong with one of the machines, and these guys are like having a bant at it and eventually say, we think this must go on YouTube. And I'm so glad it did, because the question is, why do we do this stuff? And
people are now watching this.
Let's see what's going to happen.
16.
Okay, now someone's going to put a stick in there.
We're walking away.
Somebody's got a big stick. A lot of activity. Okay.
Okay, who got hired
Intervention.
last? And who gets paid the least? Okay, we're going to try a bucket of water. Hang a bucket of water on the handle.
Actually, I think, oh, here comes a big stick.
Comes the big stick.
We're going to drown it with acid. We're going to try the big stick there. He's going to go flying across try to kill the engine with water and hit the big stick. Okay, now we're going to smother it with a tarp. We've now angered the machine.
Angered the machines.
You dumbass. This is hilarious. Okay, we're going to smother it with tarp.
Smother it.
It's going to work, I think.
Oh,
with the top, there we go.
There we go. No. No.
Uh-oh.
We've now got it in the hole spin. Oh, ole. 8 seconds. 8 seconds is what we're looking for.
Just yeah, lots of people laughing.
Oh, this is.
Made the problem worse.
This is going to be YouTube.
The film is rolling, Howard.
All right, now we're going to. Now we've irritated him, thrown him in the hole.
We've
We're
irritated
irritating people now.
It'll run out of gas eventually.
Run out of gas eventually.
Grab it. We got $50 to the first person to grab the tarp. $50 and a free lunch.
Screw it, man. I don't got any benefits.
The free lunch.
Together with your hospital fees.
Oh my gosh, we're still going now. It's not going down. It's fighting.
It's fighting.
The lions around the injured gazelle.
Okay.
No, there we go. $50 to the gentleman with the antlers.
Right, so we're going to just have a brief history look at SPC, Statistical Process Control, provide some guidelines for using it, and then we're going to talk briefly about control charts, which is one of the main tools that get used with statistical process control. So what is it? ASQ defines it as a statistical process control as a use of statistical techniques to control a process or a production method. SPC tools and procedures can help you monitor process behavior, discover issues in internal systems, and find solutions for production issues. What I really love about this particular definition is that it doesn't end or start, kind of start and end with the technique of controlling something statistically as an activity, as a visual. It kind of gets into why we do this and what we expect to do with the data that we actually get. So we really want to discover problems, find solutions to those as well. So where does it come from? There was a gentleman born in the 1800s, I think 1891. Dr. Walter Shewhart. He later became a doctor got his PhD in physics, and he worked in Bell Labs at a telephone company. And during his time or his tenure over there, he discovered and called something a theory of statistical process control. So statistical process control dates back to him. And during the 20s, he did lots and lots of presentations and published a book called Economic Control of Quality Manufactured Products. He later became known as the father of statistical quality control, the grandfather of total quality management, for those who've heard of TQM before. And it became widely used during the 1940s, during war, when they actually had to ensure that, what they were building would meet the requirements for war, and so this really popularized what he'd worked on. And some of the ideas that we've taken from his work is that all processes actually display variation. Even a well-controlled process, something that gets done over and over and over again, will have a measure of variation in the output. And so all processes display variation, but there are two kinds of variation. The first kind is something called random variation, which we also refer to in the Six Sigma world, where I'm from, as special cause variation. And this is something that is not common to our process. And we want to be able to identify it based on looking at the data and remove it as quickly as possible. And then the second part of it is assignable causes, or what we would call common cause, that we could economically discover and then be removed in our particular process. So his other ideas were that variation is a particular process characteristics that can be quantified by taking samples from a distribution and looking at that sample and allowing that data from that sample to actually speak to us. So we don't need all the data. We can get a proper sample, and we could have a look at it and make some determinations about the bigger process by looking at that sample. Also, that changes in distribution can be revealed by plotting those parameters over time. So if we take the data and we plot them over time, we will start to be able to see what kind of changes actually occur. And this formed the basis of the importance and the necessity for statistical process control, not just in life, but in our production processes. So there's a formula we like to refer to as the problem-solving formula in the Six Sigma world, and it's pretty much noted or denoted as Y is a function of X. So those with understanding of the mathematical side of function is multiplication. which means that the moment you put function in front of something, you know, it's a transformation or transformative symbol. And in this particular problem-solving formula, we always talk about the outcomes of a process as being the why. It is an outcome or an output, and this is dependent on the inputs. What are the inputs? Well, those are the X's. And the X's will be actual input variables and process variables, and they, as variables on their own, would be independent. But the moment they start interacting with one another to produce a particular output, we see that the output is then dependent on the inputs. I like to use the example of a cup of coffee. If you take everything that goes into making a cup of coffee, the cup of coffee is dependent on the volumes, the type, and the sequence of the input variables and the process variables. And if you wanted to change the texture, taste, heat, anything about the cup of coffee, you would need to go back to the X's because that's where you need to change them in order to change the profile of the output. So we use tools in the Six Sigma world as an example, but they don't necessarily belong to Six Sigma, like a fishbone diagram, where we can see, you know, the effect is then put, or the output is then put into the head of the fish. And normally in a Six Sigma or an improvement type of project, the output would be stated as a problem, a gap that we're not achieving in the output at the moment. And these are then linked, like the head of a fish is linked to the backbone and the different fins, you know, of the fish, the different bones of the fish, to likely things that are causing this effect. Differently stated, we might say that we've got a problem in the head of the fish, and we've got different causes. So you'll see different types of categories that we have in here, and we'll talk about those categories in a little bit over here. But these just don't denote the kind of things that typically are involved as inputs into a process that influence the output. So I just want to have a look at a couple of fundamentals here as I'm laying the foundation with the slides. Firstly, SPC can be considered as a control measure for inputs, but also as a monitoring measure for the output. So back to our previous slide, we really cannot fix the effect. We can only monitor the effect. I can only monitor the taste of the cup of coffee. I can't fix the taste of the coffee once the coffee is made. If I wanted to fix something, I need to control the inputs better. So that's why statistical process control is a control mechanism on the inputs that are specifically influencing their particular outputs. We monitor the output, we control the inputs. A few important factors to consider as well when I'm looking at statistical process control is that firstly, control should happen at the input level. As I've just stated, response time to out of control situations should be as quick as possible. So the measurement side of this is sometimes what I see in businesses is that they've got a chart up there, they're measuring the process statistically. When I engage and ask them, so what are you guys doing about this? I find that it's a wallpaper exercise. It's a nice chart up on a wall, but nobody's really taking that information and doing something about it. Or they're doing something about it, but the time they take to respond is too long, and therefore they're not getting the benefit of the early measurement of a particular input. So we want to be able to see the out of control situation as quickly as possible, and then we want to be able to respond to that as quickly as possible. Without being able to see it quickly and respond quickly, we're literally wasting our time doing statistical process control. Okay. Two other factors I just want to talk about very, very quickly. The one is that control limits actually come from the process, and I'll show you what control limits look like when we look at control charts, but they are different to specification limits that actually come from our customers. So we get upper and lower control limits. They're sometimes confused with upper and lower specification limits that actually come from the customer. More about that in a little bit. So why do we gather data for SPC? Do any of the folks that are online or in the room at the moment use SPC in your business? And if you can maybe just share with us, yes, you use it. This is what you use it for. This is why we do SPC.
We see in our business various processes, not your typical SPC with control charts and things like that. And then we use it more for trend analysis, basically looking at, and that's what SPC is. You want to pick up that certain control within your process is going to go out of spec before it goes out of spec. Now the control charts also, I don't really like them because I also think it's a paper exercise. We've sort of automated it in a way that it alerts us, and once it's out of spec, it rejects the parts immediately and things like that, based on the data received. But your question, why do we run SPC? Is because we want to detect out of control process before it goes out of control.
Perfect. Awesome. Love it. Thank you. Anyone else?
We're not production orientated ourselves. We've developed a system that people use to manage their business. So the way that we've developed the system is that if you use the system, it does gather information for you statistically on what the people are doing. And that in itself is going to help you to identify trends and also how much of what is being done by, call it an individual or a specific area, and what the results are. And obviously then you can, it gives you a viewpoint as to what decisions or what changes you need to make, or where you need to look at things slightly different.
Awesome. I love that, and I love the fact that you're talking about a systemic approach, to controlling process, because this concept doesn't kind of hang on its own. We don't just control things because we did the chart, right? And even if we did the chart and we did that perfectly, a few other things need to work together for us to really get control of our processes. And I'm going to show a couple of different options just now and where statistical process control fits into that, because it isn't the only tool, but it is a great tool to use where we are generating data and where it can allow us to understand our processes. So a couple of reasons I've got on here is sometimes we do it because our customers say we need to. They're looking for this as a quality metric to see whether we've delivered to them according to agreed specifications. And we also sometimes do it to monitor a process, make sure that things aren't getting worse. I'm hearing things like trend analysis. What's happening? Are we getting better? Are we getting worse? Are we staying the same? Are we remaining, is our process remaining in control as far as the outputs are concerned? And sometimes it's to learn when things have actually changed. So we might use it if we have put a new piece of machinery in, or we've changed process and we actually want to see whether the improvement has actually worked or not, in which case you want to understand what the performance looked like before the time and what it looked like afterwards. And then to use SPC, very important, in conjunction with, not instead of, but together with other improvement tools to actually improve our processes over time. So if you think about the drive with production 4.0, machine learning, sometimes we feel very threatened by these things. But if we can embrace some of these technologies, we'll find that what it does is it doesn't replace statistical process control. But what it actually does do is it begins to give us feedback very quickly on what's happening almost in real time. And when they're building things like robots and so on, or robotics into the processes, the machine is then able to translate that information into something meaningful and tell us very quickly if something is actually going on. So So we all have our different reasons for it, and it's great to have the different reasons. I kind of like this picture, so I thought I'll throw it in here. Because we sometimes led very strongly by opinions. You know, we've always done it this way, and we know those machines, and we know how it works. But before you're going to collect data to use for statistical process control, it's actually very important to think about, why am I collecting this? Because that will lead me to, am I collecting the right data? Am I collecting in the right way when I want to answer the question of why? We also then have to think about, you know, who is going to be collecting this data? How are we going to analyze it? What do we plan to do with it? And if I'm collecting it, what is the potential downside of collecting this data? Is there going to be fear, you know, when I'm expecting people to collect this as well? How do I approach that if there's fear around it? And you know, these considerations are very often not done when we set out to collect the data. We kind of just take the numbers and start churning out graphs. But this becomes a very important component of statistical process control. So there are levels of good and, you know, better versus worse when it comes to methods to controlling. When we spoke about a control system just now, the ones I've put in here in yellow are pretty much the ones that refer to SPC. Now notice that it comes up in more than one place here, right? The best way to control a process is to have a countermeasure in place where we can actually stop this error from occurring in the very first instance. So we'll never create a defect. This is where we use something like a jig, or we put something in there, and before the machine will press it, it'll first check a certain quality, and if something's wrong, it just won't do anything at all. So that's where we start talking about things like error proofing, or you might have heard the Japanese term for that, poka-yoke or poka-yokeru. You know, and that's your best kind of corrective action, is not getting it wrong in the first place. But sometimes we don't have that. You know, then I've got a second kind of corrective action, which is a flag. Something goes up, a light comes on, a noise goes, something that says, hold on, okay, we've made this boo-boo now. Before we pass it on to the next stage and create more waste, let's just first fix it. Okay, so that's a kind of the next best one. Then we've got one that says we're doing statistical process control on our X's or our Y's with fully trained operators and staff who actually respect the rules. So without properly trained operators, or without people respecting the rules, what are the rules there for? What do we do when this process goes outside of the rules? Without that, statistical process control doesn't mean anything. You can see over here, type 3 is an inspection, okay? And we know how good inspection is. And sometimes this is all we've got in business to get quality in. We've just got inspection. But what if there was a better way than just inspection? Because inspection is after the fact, when damage has already been done. And we can miss things with inspection. And then we've got SPC with fully trained operators, but obviously not respecting the rules. We've got SOPs right down the bottom here. Processes, standard operating procedures, work instructions. They're really not such a good way of ensuring quality and controlling your processes as what you might think. And sometimes these SOPs were created for other reasons. They're made as part of your quality management system. They weren't really there created at the level with the right level of detail and in the right language for people to follow process. It's more so that we can show off to somebody how good we are. And then there's the warning signal, and then there's SPC right at the bottom here, which is really just a wallpaper exercise. I've put the word decoration in here, like a Christmas decoration. Looks pretty on the walls, means nothing. Okay, so there are levels of SPC, and if we don't look at the entire system, then SPC is not helpful for us. I mean, I just put this in here, but if I asked you to find all the F's in that, I will guarantee you 100%, I'll put all my money on the line, that if I asked you all to count those F's, you would all give me a different figure at the end, most likely. And that's because we miss things. Inspection is futile. And the problem is when we're not using data that's available to us to control things statistically, we end up trying to inspect quality in. This is what businesses sometimes call quality assurance versus controlling quality in our process up front, which is always a better idea. You want to know how Toyota gets it right? They control every part of their process. They don't hand over things that are wrong or don't fit form. In our businesses, very often we pass on the bad quality because we don't get measured in quality. We get measured on producing volumes. And then I know that somebody else, or I think somebody else downstream will pick this up and fix it. Okay. And the next guy thinks that too, by the way. And the same for the lady after that. Everybody thinks I just keep passing it down, you know, and then we have these poor defects at the end. So let's just talk a little bit about prevention versus detection, because detection means nothing if it can't lead to prevention. So in the past, manufacturing depended on inspection to screen out non-conforming products. The process itself produced a lot of rework and scrap, so lots of waste, or muda, as they call it in Japanese. Okay, total uselessness. That's how they see the waste of muda. Inspection doesn't increase quality. It only affects customer annoyance. And the problem with detection is that it tolerates waste, because we build our processes assuming we will inspect, and therefore assuming the waste will work, and therefore it tolerates it. If you really wanted to get right with quality, you need strategies for prevention. And this is where we're at right now in 2023, is that we can't afford to be tolerating waste and rework anymore. So you've got to find ways to build quality into the process, something we call mistake proofing. And if mistake proofing is impractical or impossible, then control the inputs to prevent non-conforming outputs. So pick it up early. How does this look? Well, one of the ways is statistical process control at the right level of the X, at the right inputs. Prevention avoids waste. It doesn't tolerate it. So SPC is a feedback system. And let's quickly discuss the different parts of it. Firstly, the process. So we refer to the 6 M's in manufacturing. Remember that fishbone diagram that I said we'd get back to? Those were some other words for the same things. So people, machines, material, the ways of working, or the methods, or the different procedures, the way we're measuring the process, or the measurement that happens to be there, Mother Nature, the environmental kind of stuff. They work together to produce an output. So we actually want to understand the process and understand and identify which are the critical inputs that we need to statistically control or otherwise control better, that have the biggest impact on the output. Then information about the process itself. It's ideal for us to gather information about the X's, although some benefit is obtained from monitoring the outputs. So it is important to understand the output, but understand we can only monitor it. If I want to control it better, I've got to work in the input level. Think about your favorite sport, soccer or rugby or cricket. You don't win a game by looking at the scoreboard and wishing it better. By the time it's on the scoreboard, it's done. If you want to influence the scoreboard, you've got to go back to the game. And this is why they have halftime and timeouts, where they say, hold on, guys, we're missing it. We need to readjust. Our opponents are doing something different than what we've discussed in the game plan. Without that Y metric, checking the output, we may or may not respond to the game plan. But we actually want to know early on if it's working. So by the time it's on the scoreboard, it might be too late already. So there is value in the Y output being measured, but we've also got to extract the value by quickly going back to the game plan, because you can also look at the score and change nothing. And so the more often we have our data points and the more frequent we have them and the time between them becomes shorter, the more opportunities we have to reflect and do something about it. If I only measure once a month, then I've only got 12 opportunities a year to respond. If I measure once a week, I've got 52 opportunities. If I measure once a day, I've got 365 opportunities. If I'm measuring every hour, I can still change the course of things on an hourly basis without waiting to see if I've made it at the end of the day. So ask yourself this question. When you look at performance at the end, are you saying, guys, I'm really hoping, hoping and wishing tomorrow's report looks better on how we did today? Is our process controlling us, or are we able to determine with a high level of confidence, yes, actually we're in control of our process. Tomorrow will look better because we're measuring this thing every minute and every hour. Then action on the process, very important, because without action, we can't prevent anything. And then action on the products themselves. You know, this is what I was talking about just now. It's when I take action by looking at the outputs. Not the most ideal because it's already on the scoreboard. I want to be able to see it earlier on. We also talk in our business about leading and lagging indicators. A metric on an output, a Y output, is a lagging indicator. It's after the fact. A leading indicator means I can still change things so that I change the output. So when we talk about process variation or processes and SPC, we got to understand that variation happens, okay? And different processes have different kinds of distributions. Now, this is not a training session, so I don't want to go too deeply into it. But there are certain rules that we learn from statistics based on the kind of distribution that our process has. We call those the empirical rules. You're looking here at a normal distribution. Normal distribution is a bell curve. And the reason why it's got this peak at the top is because this is where your averages lie. So if I have a look at my averages, most of my data is around my average. And then as I move to the left and the right of my average, I find that in equal amounts, this variation decreases to the left and to the right. And it forms this kind of bell curve over time. Now, not all process outputs have a bell curve. Some have a different kind of curve. And if we can understand, and we're measuring it, we can understand what the behavior of our process looks like. The shape, but we can also understand how much variation occurs. Because the flatter that bell, the more my variation. The smaller or the narrower my bell, the less variation I have. The more control I have of my process, the more consistent it is at delivering things when it's supposed to deliver it. So units may vary from one to the next, but together they will form a pattern. And that's why we want to actually get data over time and start to graph that and understand it. So we can get different kinds of differs or distributions that differ. So if we have a look at these, let's say that the blue one that we're looking at over here is where I expect to see my data, and this is where I expect to see my my average. Right now, my average, my shape is more or less right of my data, my actual data, but I'm out of spec as far as my average is concerned. So this is something we would call by location. The location is different from where I expect it to be. Average is a typical location. Then we can have a problem with spread. And here's the problem with averages. Averages that we like to use in KPIs on their own only tell you one part of the story. It only tells you where's the average of my data. But when I look at all my data, I start to look at things like spread. So I could want my spread to be very narrow, but I might find that my actual data is I've got a lot more of what you guys might call outliers. I've got a lot more stuff that's just all over the show. On average, we look good. The problem is with spread. And then the third thing can be shape. So this could be that I'm expecting it to form a normal curve, but it's got a different kind of curve. Okay. So back to our Walter Shewhart, two kinds of distributions, right? Or two kinds of variations, special cause and common cause. And Special cause variation are the things that normally require us to pick up quickly if there's a problem and to do something about it. Actions can be taken by people close to the process. Special cause variation must be eliminated before you start looking at attacking common cause variation. And this is normally something that if I have proper statistical process control, it will show up in my control chart. Something's going very wrong in my output. And it's normally back to an attributable cause. Something we've changed. We've changed the mixture today. We've got a new person working the line. We've made a change to the machine. It's something that we've deliberately changed. And if you see that it's negatively impacting your output, unless you planned for it, go back to that thing and fix it very quickly. Then common cause variation comes from a process that has not got special cause. You first fix special cause and then go to common cause. And this is where a process is in control. It tells us that all our X's are actually performing as they should be performing. There's no outside influences at the moment. The process is quite controlled, but control doesn't necessarily mean good, because it can be controlled, but your customer specs require it to be tighter. Remember, I spoke about upper control limits and lower control limits versus upper and lower spec limits. Upper and lower spec limits come from a customer. It says that greater than this and smaller than this is defective. It's not acceptable. So you can have a controlled process that's out of specification from our customer. So we can't just look at control without looking at specification as well. And I'm going to show you that in one or two of the slides. So in this particular case over here, we're looking at 4 scenarios. In the first case, and by the way, the red limits are my customer specification limits. Okay, so that's my arrows. So over time, we see that this process is behaving as a normal distribution, and it's very consistent over time, and it's within customer specs. That's how we want our process to perform. Case number 2 is it's pretty consistent over time, but look at our customer specs. So we've got these defects that are outside of our customer specs, although the way we're running this process might be within statistical process control. It's out of specification. Case number 3, we've got in spec, but look at what's happening with the behavior over time. Let's say from 1 week or 1 day to the next, 1 shift to the next, 1 week to the next, 1 month to the next. We've got a change in how our process behaves. And then case number 4, it's a change in how it behaves, plus it's outside of specification. So the greatest ideal we have here is case 1. And that's what's explained over here. It's does it meet requirements and in control? That's our best case. Our other case here is, listen, we're still meeting requirements, but we've got some out of control stuff here. And if I don't keep an eye on this, I could find that things go out of control very quickly at some point in time. So one of the tools that we use mostly is control charts. And if properly used, control charts can be used by operators to in an ongoing way control a process. It can help us perform consistently and predictably. It can provide a common language. So if everybody understands the control charts and the limits that have been put there, it provides for a good way to talk to one another. It can allow us to distinguish between special cause and common cause variation. And it can serve as a guide for local action or action on a system. Okay. And then it allows for the process to achieve higher quality, lower unit costs, higher effective capacity. But that's within a system where we're actually not just using constructing it, but also actioning it on time and using it to monitor and control our X's better. So one of the ways we can do this is a run chart, and a run chart is a very simple kind of control chart. It's a running record of a process over time. Because it's a very simple way, it gives us a sense, if we look at this, whether our process is controlled or not. typical example of a process that's in control, you will know visually if you look at this, it's random. So I've got points going up and down. It's kind of random. There's no real pattern that you can see over here. There's no trends going upwards or downwards. And there's nothing that really stands out here. If you look at the variation from point to point, it more or less fits within the overall variation. So visually, we could look at this and say, you know what, there's no real major obvious cycles or trends or what we call freaks in here, you know, special causes that are coming out. So it does give us some level of predictability. But here are some of the limitations. Firstly, there's no reliable way from a run chart to differentiate between common cause and special cause variation. Okay, and this leads to two kinds of mistakes as well. Is that sometimes we ascribe variation to a special cause when in fact it's something that's common cause. And so sometimes we might over adjust for that. I'm thinking something weird is going on here, and now we make a rule, when actually that variation we're observing is part of common cause variation. But because we don't use this as part of a bigger data set and statistically control our process, we are then over adjusting. We are overreacting to something. And then we might ascribe variation to the system when in fact the cause was special. We might make a rule on a process variable when in fact the variable was something freakish that came from outside. And so our responses to these things cause more problems in our production processes. So this is probably one of the biggest wins of statistical process control, is being able to see what is special cause, differentiating that from common cause, because our reaction mechanisms are different to those, our response mechanisms. So when we do this statistically, we run some tests that allow us to be able to differentiate special cause variation. This picture merely shows 5 different rules that have been applied. And our remember our bell curve. So imagine the bell curve on its side over here. And these are the different zones. So zone C will be closest to where my average is. And then as it dissipates to the left and the right, we'll get zone B and zone A. These rules are all telling us whether we're starting to see trends forming, whether we are seeing the kind of data that's telling us something else is going on here that's no longer common to the process. And so when we run these in statistical software tools like Minitab or Sigma XL or Statistica, it can show up where we are seeing common cause so that we can identify and eliminate those causes back in our processes as quickly as possible. When we run control charts, then this is pretty much telling us certain things. You know, it tells us where our average is. It sets our control limits, and one of the tests are, is our process going beyond our control limits? That's one of our 8 tests. And these control limits are set at 3 standard deviations away from the mean, where I'd expect to see almost all of my data between my control limits. That is where they set. So if any point goes outside of those, that's statistically normally an indicator that something funny is going on here. We need to go and investigate what happened there, because it's not common to the process. But like I said, that's only one of the 8 tests. And then we obviously understand also our average range. You know, so this is a X bar and R chart. So the X bar stands for our process mean. But it's also then looking at our moving range, our range from one point to the next. How much variation is there in the deltas as I move from one point to the next? So it's my point-to-point variation, and then between my point variation as well. So this is a graphical view of what it looks like. I think the important thing for us is that our dashboard shouldn't look like this when in fact our process is burning. We should have a control mechanism where the dashboard is showing us what's really happening in our process. Okay. Yeah, and I think that's all that I have for you as far as presentation is concerned. I know we've also run out of time. I know we started a little bit late, so excuse me for that. But hopefully we've got a few minutes to just go over some questions you might have or some comments.